turn on or not. It was scheduled on my calendar, and I'm like, I knew it, didn't drop me the disc. I'm like, okay. And I'm like, I can do it. A couple hours ago, all of a sudden another email popped through, said Oshana, and I'm like, I tried to click on it, and it just said canceled. I'm like, okay.
It's weird, because I literally got an email from Todd. I said, is it still on? He's like, yep, you'll be in 112.
How strange. You're not going to walk around, are you?
No,
Okay,
no,
you
it'll
don't
be
need
very,
this.
should be pretty, oh, I don't need that?
No,
Okay,
this,
okay.
this one's wired in.
Oh, okay, good.
I have no live students, so.
Yep, I'm just gonna lecture for a couple hours.
You're right. If you write, you're going to need this light on.
Oh,
But if you're not, you can leave the light off and just turn it on when you're ready.
I probably, yeah, probably will write a little bit.
Just put that on when you're ready. Whenever
Okay.
that thing shows up.
Okay.
Other than that, you're good to go.
Start whenever?
Yeah, I was going to figure this light out for you when I get upstairs. Just give me 20 seconds.
Yeah, okay, okay. Okay, welcome. We are going to talk this class about, continue talking about modeling techniques. We'll talk about state machines tonight, and we'll get into sequence diagrams, activity diagrams, some decision tables. We're going to work our way through the different modeling techniques that we talked about last time. And so let's go ahead and begin that process. So the a good and popular behavioral model used in requirements analysis is state machines. We'll talk about this technique first. Now we'll start with just looking at what's called the automata. And just a tiny bit of theory, and then we'll get into some practical examples. But automata is basically a machine, a computer-based machine, whose output behavior, what we see looking at the machine, the output behavior, is not only due to or a consequence of the input to that machine, but also of the past history of inputs to that machine. So in other words, the input is based on what's referred to as state, system state, which is really an accumulation of past inputs into the machine. So it can be characterized by an internal state, and that represents, again, the past experience, things that have happened to this machine that are important for it to remember in the past. So it's, and then the current input affects the future behavior based on that system state. You can draw a very simple automaton or state machine diagram this way. This is something that a simple graphical representation of a state machine to manage turning on and off a lamp. And we'll get into some of the symbology later, but basically this is the first state, or the initial state, is indicated by this dark dot that points to the initial state. The initial state is lamp on. And once I get to that initial state, if I stimulate it with an input called on, I'll go up to this new state called lamp on, okay? If I hit off from this state, I go back to the lamp off state. That's simple enough now. But again, the behavior of what happens when the system gets the input on or off is dependent on the state. So this system has one state called lamp off, one state called lamp on. If I'm in this state, if I hit the on, I go to lamp on. But if, as you can see up here, this is a little bit hidden here, that says on right up there. If I'm in the lamp on and I hit the on, if I receive the on input, I stay in that same state. So again, it's something different happens depending on the state I'm in. Likewise, if I'm in the lamp on state and I receive the input off, I go to the lamp off state. But if I'm in the lamp off state and I get the off input, I just essentially stay in the same state, ignore that input, stay in the same state. So that's an example of a very simple automaton or state machine diagram with the simple behavior of a lamp. So again, just a little bit of theory. You can define a state machine by a set of inputs, a set of outputs, a set of states, a set of transitions. You could also, and we'll talk about this later on, talk about an extended set of state variables. Those variables essentially help you realize the state that we talk about up here. We'll go through some examples. We'll have an initial state designation like this, initial state designation, and also there's a final state designation if I'm going to terminate the automaton. Or again, the automaton is, for this discussion and requirements, think of it as a fancy word for state machine. So an extended state machine, sometimes called a Mealy state machine, is defined by these different tuples or inputs or combinations, and we'll talk about some of this as we go forward. A graphical way of showing this is shown here. So we have, again, a very simple state machine shown here. We have the initial state, called the initial pseudostate. That just basically means this symbol is pointing to the initial state. That's a state. Ready is a state. Again, state is a condition of the machine where I need to remember that something has happened in the past. In this case, that I've entered the ready state, that the system is ready. Ignore the top state for now. This is more popular when we get into state charts, but for now I'm going to ignore the top state, sometimes called the superstate. This is the state I'm interested in right now. Now, from a state, we can show a transition to other states by a trigger. In this case, stop. Now, I will actually use other terminology other than trigger. In this case, trigger is stop. The transition, it's a transition, as shown here. The transition with a trigger stop. Sometimes I call that an event. And this is the action. So with the stop trigger, I then get an output or an action. In this case, set a variable control equal to 0. So the way you'll see this normally is with the event slash and then the response, and they'll become a little bit clearer as I show you more examples. So the transition with a trigger and an action, again, sometimes I call this an event and a response. And then if this machine terminates or stops, then that's indicated by this final state here, just this double circle thing. That indicates termination. And you can get there from more than one state. If there was a specific trigger from the ready state that took me to the final state, I can show it likewise coming from ready and into the final state or the termination state. So those are some of the key components that make up a state machine. Okay, now in general, state machines are very good for describing event-driven systems with very discrete behavior, states, if you will. It's inappropriate for modeling continuous behavior. So if I'm trying to model something like this, this analog or continuous type behavior or signal, it's going to be very difficult to do that unless I somehow find a way of making it discrete, either by sampling this or looking at it periodically. But continuous, it's more difficult to model continuous behavior using this type of machine. That's why one of the reasons that the finite state machine, there is a finite states, which means it's got to be essentially discrete in its behavior. So event-driven behavior. Now an event, think of this as a type of observable occurrence. Observable meaning from the someone looking at the system can notice this event happening. Dropping a coin into a Coke machine, clicking on a icon. These are events. So they're interactions, synchronous. They can be synchronous object invocations like a call event, or an asynchronous signal reception like a signaling event. Something signals, provides a signal when some asynchronous event happens. Like for example, if you click on an event or button, an icon in a user interface, that's asynchronous. It doesn't happen synchronously at some predefined amount of time. It happens asynchronously. Those are examples of asynchronous signal receptions. It could also indicate the occurrence of time, an event or a timer expiring, 3 o'clock in the afternoon event happening. So you can, event-driven behavior is also very commonly associated with time instance or change in some time. And then other event instances, things that, something happens at a particular time. It doesn't necessarily have a duration, like for example, 3 o'clock p.m., but it is it's an event instance in that sense, that it's just indicating that something has happened. Okay, so the behavior of what? There's anything can manifest itself as event-driven behavior. I'm not going to talk a lot about UML, although we've already talked about the fact that there's no continuous behavior supported. In practice, it'll mainly be the behavior of software components or objects, and we'll talk about some of these. Anything can generate behavior, as we'll see in a second. So modeling software with finite state machines is very useful for requirements analysis and requirements gathering. We can use mathematical models to help us depict software systems from a usage perspective. We'll talk a little bit about that. We didn't use mathematical models, but we used usage models earlier. More sophisticated models like finite state machines are used for internal and external behavior. That's really the key thing here. So by constructing the finite state machine, a finite state machine is just a state machine with obviously a finite number of overall states, making it discrete. The finite state machine really forces us to think about the sequence of functionalities that describe complex behavior. And so from a requirements perspective, this is very important. That's what we're trying to do, is identify specific and potentially complex sequences of functionalities that make up the behavior we have to specify and ultimately implement. You can trace the transitions of a state machine that kind of force us to then understand the set of input values. And those input values have to be sequenced in a very specific manner in order to provide the transitions to occur the way we want them to. And I know this is sounding technical. I'll show you a very practical example in a minute. So we can trace pretty complex computations with these state machines. And they're also really good for testing. Some of the things we're going to do in requirements analysis, these same models are very useful as we get into testing. And I'll talk also about that as well. We can use this to help identify the major states of a system, or even some that are missing or potentially incorrect behavior. Looking at the transitions. Each transition, by the way, of a state machine could be considered a requirement. And then also possible input and output, something missing or extra or incorrect. It's very good for quote unquote testing your software prior to even having your software ready and available. So the informal state machine, for a light switch, I'm in the on state. I can hit, let's say, hit a toggle. We'll call it flip. I hit it once, it takes me to off. I hit it again, it takes me to on. This can be represented in a matrix. If I'm in the on state and I hit flip, I go to off. If I'm in the off state and I hit flip, I go to on. In that sense, this can completely represent the diagrammatic version if we choose to do it that way. And for some mathematical analysis, it's good to do it that way. So this state machine approach, we can partition the system by states. In this case, we have 2. And we can develop tests for the transitions. In this case, the transitions are really easy, but I can basically say, from a test case perspective, hey, if I put the system in the on state, hit the flip button, and the resultant should be I'm in the off state. So it's pretty easy to design test cases for this. Again, the formal definition of a deterministic, there's some non-deterministic behavior I'll talk about later, but from a deterministic finite state machine, again, set of states, set of inputs, there's a transition rule where I have a set of states, cross product with the inputs that leads me to a new state. And then, of course, we have these designated special states called the initial state and the terminal state, or terminate state. There's another, this one here introduces Moore machines. They're very similar to Mealy. I'm not going to get into the difference between a Moore machine and a Mealy machine. It's not important for requirements engineering per se, so we won't spend a whole lot of time on that. Here's another state machine. That's a very simple example. This machine accepts strings of A's and B's and that contain exactly 2 A's and then terminates with an A. So I can create, in this particular case, I've got states 0, 1, and 2. Okay, 0, 1, and 2. 0 is, in this case, the initial state. Now, if I were to do this properly, I can put that little beginning dot that I showed you earlier, this thing here. Let me go back. I can put that dot, the initial pseudostate, and I can point that to state 0 as the initial state. The final state in this simple machine is marked as 2 prime. The inputs are A and B, and the transition rule is the following. I can say, if I'm in the 0 state and I get an A, I go to the 1 state. If I'm in 0 and I get a B, I stay in the 0 state. And I can do that for the 1 state too. If I'm in 1 and I get an A, I go to 2. If I'm in 1 and I get B, I stay in 1. And I can represent it by this matrix as well. Again, if I'm in 0, I get A, I go to 1. If I'm in 0 and I get B, I stay in 0. If I'm in 1 and I get A, go to 2, terminal state. If I get a B, stay in 1. And 2 is not defined right now. It's the terminal state. I'm going to leave it undefined. So that's how you would represent it with this matrix, a transition rule, state machine matrix in a diagram form. Really, all these apply to these simple state machines that we're trying to build up. So the general guideline to constructing a finite state machine: collect the information for constructing it. Again, we're going to start with initial requirements. We're not going to spend so much time on design or spend a lot of time on testing. These state machines can transition through the whole life cycle, if you will, so you can even look at these and apply these when you've got code, if you're doing white box testing. We'll focus on the requirements perspective. And then the construction of your initial machine, you have to identify the states, the transitions, the inputs, and the outputs. And then we're going to have to go through validating that model, refining it or simplifying it, and modifying it as we go forward. So let me start with, I'll start with a very simple example, walk you through it. Turn the light here. And what I'll do is I'll go down to the desk camera here. Okay, so what I'm going to do for this little exercise is walk you through, again, starting simple here. Let's just focus on a Coke machine. And I'm going to make this Coke machine pretty simple. Let's draw a simple diagram of this Coke machine. So there's going to be, I'm going to put a little place to put coins. Okay, I'm going to have the select button to actually get my Coke. My Coke will drop down over here. I'm going to have a, this is the change return button that I use to, if I decide I don't want my Coke after I put some money in, I'm going to get my change return. I've got a some power I have to apply to this, and when power is applied to this, I'm going to get a little red dot that tells me that the power is on. So very simple machine. Now let's define the software state machine that controls this. First of all, what I want to do is let's draw a very simple diagram that represents the inputs and the outputs that I was mentioned that we needed for this machine. So what would they be? Again, here's my Coke machine. I'm just going to leave it as a black box. And now I'm going to look for the inputs going into this, the outputs coming out of this, and identify what those are. So what would be some of the inputs or events that would drive behavior of this state machine? Many times, you can tell by looking at the interface here what they might be. For example, one would be power. If I turn power on, it's going to have, it's needed to get the machine into some state. The coins, now I'm going to simplify this a little bit. I'm going to say that the machine can only accept quarters, okay? And I'm going to say that a Coke, again, just to constrain the problem, is going to cost 75 cents, so 3/4. What else? What other inputs do I have? I've got the power, coins. I've got change return. That's needed. Get my coins back. And I've got the select. Okay, coins, change return, select, power. Now, what are the outputs? Well, the one output would be, if I put in my coin, select my Coke, I get the Coke down here, so one output would be a Coke. How about, what else? Well, one output, visible output, if you're looking at this, is this power on. The red light is an output, right? Is there anything else? Yeah, there would be. I mean, if I hit change return, let's draw a little change return area down here. If I hit change return, I'm going to get my coins back, right, as an output. I hit the change return, I get the coins drop down here. This is where the Coke is. This is my little Coke, and this is my quarters. So another output would be change, right? Okay, so if I were to take this description, high-level specification, say from a customer, they want to design a very simple Coke machine for the very low-cost market, and you can turn that into a high-level mathematical model, not mathematical model, but just high-level model. First, by looking at the boundary diagram, which is shown here. I have inputs, and I've got outputs, and that's a good first start because I need these things to start the construction of my initial state machine. Now, as I begin this definition of a state machine, we have to. I like to approach this by looking at what we talked about earlier, which is use cases and scenarios. And so, one use case obviously is going to be, they're pretty simple for this, is going to be basically different ways of getting a Coke, right? But let's take the following scenarios. The following scenarios are going to be applied. The first thing is I'm going to put the, let's say I put the precondition is I'm going to, that the machine is powered on. And then actually, you know what I'm going to do for this? Just to add a little bit of, excitement to this. Let me go ahead and do this. I'm going to add right here a little display, and that display is going to show how much money I've deposited. So let's do that. Let's put a display up here that just shows how much money I'm depositing, okay? That'll make it a little bit more interesting. So now, one scenario could be, I'll go through this quickly, we'll call scenario one the name would be, just get a Coke. And what the way this might work is that the actor would walk up, the machine's already powered on, the actor would deposit a quarter, right? You can only take quarters. And then the actor would deposit another quarter. By the way, when the actor deposits a quarter, if you're developing a use case scenario, the system would do what? The system would display 25 cents with this new display requirement I added. Then the actor deposits another quarter, system displays what? 50 cents. And then the actor deposits another quarter, and the system displays 75 cents. And then the actor hits select, giving my Coke, and the system drops the Coke. So let's say that's one scenario, right? This one would probably be, we'll call this a kind of a normal scenario, based on the work we did with scenarios in the previous class. Okay. Now, what can we decide would be? We'll call it an abnormal scenario. And we can draw it like this, right? This is the actor, and this is the system. So an abnormal scenario could be, The precondition, again, could be the system is on, okay? So an abnormal scenario could be actor deposits a quarter, system displays 25 cents, actor deposits another quarter, system displays 50 cents, and now the actor decides he doesn't want his Coke anymore, he ran out of money. He thought he had 75 cents and only has 50 cents. So the actor then hits the change return because he has to walk away. We'll call this the no Coke, sorry use case. The actor hits change return and the system does what? It drops change. Okay? Kind of a simple abnormal scenario. So I've got the normal scenario. Actor puts in a quarter, system updates the display, actor puts in another quarter, 3 quarters, actor hits the select button and he gets his Coke, he walks away, he's happy. The post condition could be, the Coke machine is back in the initial state, or probably a better way. That sounds too implementation specific. We'll say the Coke machine is displaying welcome. Okay, back at the initial state, displaying welcome, and that could be post condition. And here's an abnormal state where the actor gets partially through, decides he doesn't want that or can't afford the Coke, hits change return, and he gets his change back. Okay, now let's talk about how we can design a state machine for this. We've got some interesting information here. We've got a boundary diagram. We've got some couple use case scenarios here, an abnormal one and a normal one. So how do we create this machine? Now again, if you think about the fact that a state in a state machine is something where the system has to remember something that happened kind of in the past. So important things to remember, okay? So what would kind of we talked about this concept of initial state and terminal state. So what might this look like? Well, the initial state, how would we get to the initial state in this state machine? Well, from a software perspective, we'd probably get to some initial state by turning the machine on, right? So we'd probably plug this into the wall and the system would boot up and come to some initial state, and the display the software would have, show some welcome, sign on the display and wait, the power light would be on. It would be waiting here and just waiting for someone to walk up. So we can represent it this way. We'll have, let's start off with our initial state indicator. So we know that this is the initial state, and something is causing the system to transition to this initial state. What do we want to call this initial state? First of all, what gets us to the initial state? It's probably what? Power, plugging it into the wall. So that's a stimulus that gets to this state where the system is powered up. What do we want to call the state? Let's call it the power up state. Okay, and if you go back to the boundary diagram, so power, this input is what stimulates the system to get to the to the initial state. Now, what does it cause any outputs? Does this power on cause any outputs? Well, yeah, it does. What happens when you plug this thing into the wall? Two things happen. And again, by the way, these requirements could we're going through this exercise to try to find some of these hidden requirements. So some of these we may have to derive as we go along the way. But when you plug this machine into the wall, a couple things could happen. One is the power light comes on, right? Another thing is the display goes to welcome, right? Two observable outputs, and we have them documented here. We have power on and display. So how do we represent that in this diagram? Well, we can just put a slash after the input, and then we can list our outputs. So we can say, actually, I don't like this power on. It doesn't sound right. Let's instead just call this red light. It makes it more obvious. So the power on, the two outputs are red light and what? The display. And we set the display to say welcome. Okay? Now let me show you first of all, let me show you the generic form of what we're trying to do here. If you're going from one state to another state, we'll call this state S1 and this state S2. What causes me to go from state 1 to state 2 is an event. Generically, we're going to call this, we'll call this an event, and then we'll put a slash, and then any observable outputs from this event happening from this state, we'll refer to that as a response. So event and a response, okay? Anything that goes from, any arc has something causes that to happen. That's the event, and there could be a response from that event. Now, if there's no response, we can go like this. If the response is no observable output, there's no output that we can see or need to be aware of, we'll go like this, event / null. That makes it clear that there is no output. Null just means that's equivalent to saying there's no output. Okay? So we can use null. So back over here, we follow that same E/R. Over here we have power, the E, the event, slash. In this case, we have two outputs, red light, and we set the display to welcome. So now we're in the power up state. That's the precondition, powered on, or the system is powered on. To make this thing even more clear or more accurate, more complete, we could put the system is powered on. We can say, if we want to, that the red light is on. And we could also say that the display is set to welcome, right? So we could, if we wanted to get more complete in our precondition, we could say, yeah, the system is powered on, the red light is on, and the display says welcome. That's a great precondition. And that represents the system when it's sitting at this state right here. It's powered on, the red light is on, the display is set to welcome, okay? So that's that's our precondition. We're sitting there. Now, let's go to the scenario. What do we want to show? What's the first thing that happens? The actor drops a quarter in. What is that? Well, up here it says that the quarter is an input. So the actor hits an input or causes an event to occur. What's the output? The system displays 25 cents. So how would we show, first of all, is this worthy of a state? Do I need to, let me ask it another way. Do I need to remember, does the system need to remember that that this event, quarter, has occurred? I think you would probably say yes. The system has to remember that because, why does the system have to remember that? Because if I'm going to spend 75 cents for a Coke, I need to know how much money I'm depositing or remember how much money so I can know when to give him his Coke, okay? So I have to remember that. So if I have to remember that, that means I need a new state to remember that. Okay, to remember something new, some other thing that has happened to this system that I need to remember. What is that? How do I, well, there's an event that occurs from this state, okay, that causes that to happen. The event is I put in a quarter, that's the event. And the response is what? So the response is going to be the display equals and I'm going to say 25 cents. It's going to display 25 cents. And so what would be a good name for this new state? Let's just call this the 25 cent state. It's an indicator that I've deposited 25 cents. Let's go back and follow the scenario line by line. What's the next step? The actor deposits another quarter. System displays 50 cents. Okay, how would that look? Well, I'm here. That's where I am in the story. Now I have to deposit another quarter. I think I have to remember that too, because again, I'm counting up to 75 cents in this case. So I'm going to have add another state, a quarter. Again, from the state, it's just another quarter. What's the response? It could be display equals 50 cents, right? Let's call this state 50 cent. I think there's someone named that out there in the music industry. See what's going on here? So we have to remember something else happened, so we're gonna do that. How about, let's go back over here. What's the next step? Actor deposits another quarter, a third quarter, and now system displays 75 cents. So again, I'm just implementing this one scenario. So let's I think I have to remember that too, right? So let's go ahead and put that in here. Again, a quarter is going to take me there. In this case, I'm going to display 75 cents. We'll call this the 75 cent state, okay? Now, again, back over to the scenario. What's the next step? Actor hits select, and then the system drops the Coke. Okay, so from this state, the actor hits select, and the system drops the Coke. Now, do I need to remember that happened? Let's hold that thought for a second. First of all, what's the stimulant, the vent? It's select. And what's the output? If I'm in this state and I hit select, what's the output? The output is I get my Coke dropped. It could be a signal sent to a mechanism to drop a Coke, whatever that is. That's we're going to call that the Coke response. Again, it shows up over here on my my Coke is an output. That's think of that as an output. It could be a signal to something that drops your Coke or what have you. That's you get your Coke response. Okay, I've implemented this scenario. Okay. What's the what else do I need to do? Let's go back over here. I have this arrow kind of going out into nowhere land here. What has to happen here? Do I have to remember that occurred? Or after the guy selects the Coke, is there another place I can go, or do I have to go to this state right here? First of all, does this system terminate? By terminate, in this case, it would be, does this system ever turn off and stop working? Right? It doesn't, right? What happens after you go up to a Coke machine and you get your Coke, and then the next person comes along behind you? What's he staring at? He's probably staring at the system just as if nothing happened. You walked away, you've got your Coke. The machine doesn't have to remember that you got your Coke. It just now goes back and waits for the next person. So really this system just keeps on working. My Coke machine just keeps operating in kind of an infinite loop. I get my Coke, get my select, get my Coke, walk away. The next guy comes up. It's waiting for to do the same exact thing, right? So I have to, how do I represent that here? Well, rather than go to a new state, I don't have to remember that someone else got a Coke. I just have to get the guy his Coke and then start all over again. How do you represent start all over again? Well, we can represent that by sending this right back to the initial state. That just says, I hit the select, I get my Coke, and I go right back to the initial state and wait for the next person. What's the system in this condition? Well, it's got the red light on displaying welcome. That's what this is, and which is what I'd like to see here. And the post condition is I'm displaying welcome like I'm saying here, waiting for someone else to get their Coke. Okay? Scenario number 1. Let's go to scenario number 2. Remember this one? We call this an abnormal scenario. This one was actor deposits quarter, a second quarter, then says hey, I'm out of money, hit change return, and then get my money and go on my way. So how do I represent that in this machine? I can use, by the way, a state machine can be used to reflect all behavior. I don't need a separate state machine for each scenario. I can put all of my scenarios in one state machine. I may have to augment it now because I've only considered one scenario here. As I consider more and more scenarios, I can add more to this. Actually, what we're going to ultimately need to do is show a state machine that reflects every possible scenario. And I'll show you that as we go through this. But so if I were to follow the same storyline, I'm in the initial state. I deposit 1 quarter. And I display 25 cents. I deposit another quarter, and I display 50 cents. Now at this point in time, instead of depositing another quarter, I want to get my money back. That's the change return. So instead of the quarter, from this state, the actor has to hit change return. What happens when you hit change return after you deposited 25 cents? Well, the machine should give you the change, right? So the response is going to be, if I were to go back to my boundary diagram, the response is going to be change, right? So let's put that here, change. And where do I go? I deposit my change. Again, I don't have to remember that I've done that. I just have to start all over. Start all over is one of these two. Deposit, give him his change, go right back as if nothing ever happened, right? So that's scenario number 2. So I've done my common scenario, I've done an abnormal scenario. Well, as you can certainly surmise by now, there are some other scenarios we can consider in this. For example, what happens if I hit change return after 25 cents? Well, you'd expect similar behavior. Change return after 25 cents, would do the same thing. I hit my change, go back to, if I hit change return, I send the user their change and go back to the initial state. And actually, even at 75 cents, I could decide that, you know what, if I hit change return, decide I don't want my Coke, I'm going to get my change and go back to the beginning like that, okay? But even that's not complete. Can I also hit change return in the initial state? I can walk up to a machine that was powered on and hit change return. What happens then? For similar behavior, let's assume if I hit change return from the initial state, / I'm going to put change again, because that's the output. Now you may be saying, yeah, but there's no change in the machine here. Well, that's fine. Change here, change, I'm using the same response, change, 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 change. I'm not saying return 25 cents, return 50 cents, return 75 cents. I'm saying send a message, send an output called change. This can be a signal, to a hardware component that just drops a tray and returns whatever change is in there, even if there's nothing in there. So change is just a signal that indicates empty the change tray regardless of how much money's in there. I mean, someone could have come along and deposited 10 quarters in there, and here you are starting at the beginning. You can just maybe check, like some of us did when we were kids, just hit change return on every phone machine and every other change return opportunity. There might be some money in there left over, so you just don't worry about it. Just change is just a message sent to a tray to drop whatever's in there, so that we can do that. What else is missing here? What if I hit select from this state? What happens? I only have 25 cents in the machine. What if I hit the select button? What do I do? Well, I should probably ignore it or do nothing. You don't want to really do anything. You certainly don't want to give them a Coke. You don't want to return their money. You want to just ignore it. Select has no behavior, nothing happens if you don't have enough money. So here I can do, this is just essentially meaning ignore it. If I hit select, this is getting very busy, I can just ignore it. I'll put null in there, okay? And what happens if I hit select here? Well, again, I can ignore it. I'll loop right back around and ignore it. That's select. I don't have enough room to write in here, but that is select/null, okay? What if I hit select here? Same thing, right? I ignore it, but I can have another thing out here, select, and I ignore it. See how complicated this is getting? Just to add all for completeness. There's another thing I'm missing. What if out here at 75 cents, how do you want to describe the behavior if somebody enters another quarter? How do you want to deal with that? Well, you could deal with it in a couple different ways. Let me show you a couple ways we can deal with it. So here's my 75 cent. Here's my stimulus coming in. It's a Q, and I'm going to display 75 cents. And now I'm in the 75 cent state. Now I already showed that if I hit change return, I'm going to give the change. And I also know that if I hit select, I'm going to get the Coke. And both of these go back to the initial state. So I showed you that behavior on the previous picture. I've just simplified this a little bit. But that's basically what's happening. Now, the rest of the state machine is over here somewhere. Now, another quarter. What do I do? This is where you might find some of your hidden requirements by going through this process here and thinking about what happens when these other interesting sequences of inputs happen. So I've got my 75 cents. I can easily get my Coke. I can, of course, ask for change. If I add another quarter, here's what I could do, okay? There's a couple different alternatives. One would be I can go to a state where I return extra. So basically in this state, if I have another quarter, I can add more behavior. I can say, rather than just hit change, why can I not use change? Because as we said back here, change is just a signal into to drop whatever's in the change tray or in the in the input tray, in the quarters tray, if you will. So I can't say change or they're going to get all their money back. This would be like if I entered $1, I get all 4 quarters back. I would have to almost invent something new. Like I have to invent another output called return quarter, right? Or I could do this, which basically the return quarter would mean, what would I have to do to this diagram? I have to come in here and add another output called, return quarter. I could do that. Let's go. What other options do I have? Actually, I could actually do that and maybe even get away with doing something like this. If I add a quarter, I can do quarter, return, quarter, and then stay in the same state, right? I could do that. That would actually get rid of this. Now what I have to do here is I have to add an extra output. But with this, the user gets their extra money back. I deposit 75 cents. If I put another quarter, chink, there comes my quarter. Sorry, you entered too much. What else could you do? You could also do behavior that's different. It's how the toll booths on the Long Island Express used to work, and that is if you throw in extra money, I do this, quarter, null. What does that do? Now, what does that do? What's the difference between this and this? If I'm in 75 cents, quarter, return quarter, which means if you drop in another quarter, I'm going to return that one quarter and then stay in the same 75-cent state. This one does what? You drop another quarter in, null. What does that mean? That means, you know what? I'm going to ignore it. If you put in too many quarters, that's your problem. I'm just going to, I'm going to keep it. Right? So this is the way of making extra money. This is being fair and equitable. You can, each of these is a different requirement. By the way, on a state machine, you can't, I mean, this, you'd have to have one or the other. This is an or. You can't have both of these. I'm just showing you different examples, different alternatives. This would be kind of like requirement 1. This would be 1, you know, 1 prime. This would be, they're different. Call it requirement 2 if you want to. So we have these different requirements. You have to pick which one is useful to you, which one do you want to use. Well, you have to pick. This one says I'm going to eat your quarter and you're not going to get it back unless you change return. This one says I'm going to return your quarter if you enter too much. It's a decision, and it may not be obvious when you're looking at this picture or whether you're reading the requirements, what happens when you have these weird scenarios like this. This is where you start getting into deriving some requirements. This is where you find some of those hidden requirements, and you have to define them when you find them in order to be able to complete the model and move forward. And so this example shows where, hey, that behavior, it's not obvious what it is. You have to make a choice, and you could go in either direction. That's kind of what we're trying to show here is these different alternatives. I'm not saying one is right or one is wrong, but you have to document which one you want to use. Which behavior do you want? Document it. It's a derived requirement, and tell me how you want your machine to operate. Now there's, so basically the rule here is that you need to consider, when you have that's why it's so important to draw this boundary diagram. When you have this boundary diagram, you have to consider what happens to this system. What is the behavior and the outputs? What's the behavior of this system when I get these inputs, these stimuli, in every state of the system? So in other words, when I'm in this state, when I'm in this state, this state, this state, what happens when I get, every single one of these inputs in every state? What do I do? You can show this on a, kind of a matrix as well. If I have a matrix and I've got some states here, and the states, I have a power up state, and I have a 25-cent state, and a 50-cent state, and a 75-cent state, right? And then I have these different events. What are my events? My events are power, quarter, change return, select. Okay? Let's look and draw a little matrix here. Okay? And the way you can work through this is you can create a matrix form of this same state machine. So you can start with, if I'm in the, actually I can start with the empty state, but let's start with the power up state, which is this state right here. If I'm in that state, what happens when I get the power? I know we didn't talk about that, but let's talk about this. I'm in the power up state. What happens if I get another power up stimuli. Well, since I'm already in the power up state, if I get a power, like another power up signal, you know what I'm going to do? I'm going to stay in the power up state, and I'm going to ignore it, null. Okay, that just basically means if I were to show that diagrammatically, again, I'm out of room here, but that just means if I'm in the power up state and I get power, I'm going to ignore it. That's basically what that means. So that right there is what this is saying. What if I'm in the power up state and I get a quarter input? What do I do? So power up state, I get a quarter. What do I do? Well, I go to the 25-cent state and I do a display update, right? What if I'm in the power up state and I get a change return? What do I do? Well, I stay in the power up state, and what do? I send that message, that signal to change, to drop the change. And what if I'm in the power up state and I get a select input? I'm going to ignore it. I'm going to stay in the power up state and I'm going to ignore it, null. So basically, this first line this way, this first row, is I'm in the power up state. What happens if I'm in this power up state? If I get every one of these inputs, what do I do? And that takes me down this row like that. What if I'm in this 25-cent state? That's this state right here. Let's have the same exercise. If I'm in the 25-cent state and I get the power, not power off, just the power on, I'm going to ignore it. So I'm going to stay in the 25-cent state and ignore it. What if I'm in the 25-cent state and I get a quarter? I'm going to go to the 50-cent state and I'm going to display 50 cents. What if I'm in a 25-cent state and I get a change return? I'm going to do what? What happens here? I'm going to go to the power up state and do change, right? So if I'm in the 25-cent state, if I get a change returned, I go to the initial state and I drop my change. That's what this is saying, power up, change. And then if I'm in 25-cent state and I get select, what do? I'm going to stay in the 25-cent state, ignore it. Okay? And then you do this for for this whole matrix. So what if I'm in the 50-cent state and I get power? I'm going to ignore it, same thing. If I get a quarter, I'm going to go to the 75-cent state and I'm going to display 75 cents. If I get a change return, I'm going to do what? I'm going to go to the power up state again and do my change. And then if I'm in the 50-cent state and I get a select, I'm going to stay in the 50-cent state and ignore it. And then finally, 75 cents, if I'm in the 75-cent state and I get a power, I'm going to ignore it, stay in the 75-cent state and ignore it. If I get a quarter, what do? We're going back and forth on a couple different options for this, right? Let me do this. I'm going to use the cheapo way. I'm going to try to make more money. So I'm going to say, if I get another quarter, I'm going to stay in the 75-cent state and ignore it. What is that? Which, let's see, let me go back to my picture here. So what option did I just choose to do? I chose this one, right? If I'm in the 75-cent state and I get a quarter, I'm just going to stay there and eat it. So in other words, I'm going to keep it. What happens if I'm in the 75-cent state and I hit change return? I'm going to go to the power up state and return change. And then finally, if I hit select from the 75-cent state, what do? I go back to the power up and I get my Coke, right? So I'm over here, I'm in the 75-cent state, I hit select, get my Coke, go all the way back to the beginning. So power up, Coke. Okay? So for states, and events, next state, and response is what goes in here. So this whole thing will be next state and response. That's really what that indicates right there, okay? So that's what, that's the matrix form of this diagram that we've just created. Now, a couple of useful things here. If you can validate the diagram you do. Diagrams are good for reviewing these models. You can try to simplify them by eliminating states, which is good. Anytime you can make this smaller, that means the amount of software gets smaller. You could, diagrams are great for looking at stuff like that, but this matrix is also good. And one thing that I use this for is if you do a matrix representation, if you ever see any state where it's empty, there's nothing in it, that means that you haven't defined a requirement properly. That means that there's some behavior that is undefined. So when you build this matrix, if you have something that you don't have defined, it's an incomplete specification. Decide what you want to do. That normally means if one of these is blank, it means you're missing an arrow off of a state somewhere and you got to go define what that behavior means. Okay? And it's important from a requirements perspective because when you have this model, when you build a state machine, generally, every arrow, every arc, I'm in this state. You know how this goes, right? I'm in this state. I get this event. I go to that state and produce this response. So every arc that has an event and a requirement that takes me from one state to another state, this is actually, you can consider that to be a requirement. And if I have, obviously if I, so basically in this system, I can say I've got, one requirement, 2, 3, at least 4 requirements, and I can write these requirements, in a way that basically says, hey, if I'm in this state, whatever that state is, if I've deposited 25 cents and I deposit another quarter, I'm going to display 50 cents on the display and update my counter or whatever. I mean, these can all be stated as requirements. So think of it as this way: is every arc in a finite state machine could be essentially a requirement. Okay, so think of it that way. So in that sense, this matrix, has, what, 1, 2, 3, 4, 1, 2, 3, 16 requirements. You could write and specify in that, event response manner if you want. But it's a good way of looking at it, because if you look at this as being, hey, these are 16 requirements, then when we come to testing, you want to make sure you cover all the arcs to know you have a complete set of tests that cover all the requirements. So that's why it's also useful for testing. Okay, so that's the that is my example of a simple state machine for a Coke machine. And I've got some more slides, goes into a few more details, but that's really, if you grasp those concepts that I just talked about, you should be okay. That's kind of what we kind of did here by going through this process. This is another example where if you had, this is getting a little bit more detailed. If you had some pseudocode, or basically a detailed, think of it as it's not code, but it's detailed specification, where you're trying to at a detailed level specify behavior. It's shown here. This is an example. Initialize sum in n as integers of 0 value, ask for and read in N, check the validity of N. If N is valid, then you're going to compute a sum and print out that sum and terminate. If it's invalid, then you're going to issue a message and return to step 2, where you ask for and read in N. So what is this, how would you represent this? So here's a simple diagram for this detailed snippet it's not code, it's pseudocode, but I'm going to first initialize sum in N, that's step 1. Let's just go through this quickly first, and then I'll come back and give you a few more details. And then ask for and read in the value of N, so I'm going to input N. Check the validity of N, so I'm going to validate the input. Oops. If it's valid, compute a sum and print out that sum and terminate. So if it's valid, compute the sum, print it, and then terminate. Invalid, issue an error message, return to step 2. Invalid, error message, return to step 2. Now, that's that's a partial. We'll call it preliminary state machine. What's missing on this that we just got through talking about? Well, we don't have details of events and the responses. We should have something pointing to the initial state. There's some things missing on this, but at a high level, at a preliminary level, if you look at these steps, you can see how we implement that in this state machine, okay? Diagrammatically, it's almost easier to grasp what's going on as opposed to trying to read this sometimes. This could be an improved one. What if I initialize sum in N, and then for valid N, I compute the sum. The sum goes, I print the sum and terminate, so I essentially move a few things around here. Once I input N, I do the validation there, send it along valid N. If it's invalid, I just spin and input a different N. If it's invalid, issue an error message and return to step 2. If I have that in step 2, I could validate it there. If it's valid, push it on. If it's invalid, input another one. So you kind of can condense it. We'll call this, could this be an improved, it says here, validate input and error message states have disappeared. Do you want to put it back in? Sometimes it's better showing fewer states, simplifying it, getting rid of some states. I mean, do I need, for example, issue a separate state for issue invalid message and then go right back to input? Or can this be a response? Maybe this is another way to draw this would be how would you do if I'm invalidated? Let's assume I had a separate state for input, a separate state for validated input, and now what are the options that I've got here? Let's take another quick look at this and see what options I've got. So let's go to the desk again here. So I've got this this input N, and then I have this validate input happening here, and then I've got this issue invalid message, which is an output, and then back up here. Okay, that's what that picture shows, and then there's another. So couldn't I just simplify this and say, okay, I mean, I'll use the same diagram. Couldn't I just do this? Couldn't I just get rid of all this and instead have this? I can have, so this would be valid. Okay. Could I also just have this issue invalid message okay, as a response to a invalid check out of this validated input. Because in the previous example, this is valid, this was invalid. And so why do I, do I need to really go to a separate state just to then issue an invalid message and then on completion go directly back to N? There's no really defined event that takes me there. I just have to do an internal event. Or can I simplify this all out and just have two states? Simplification is good, and when you can simplify a state machine, eliminate a state, it makes the complexity go down and makes the whole thing easier to understand and validate. There's a lot of good reasons why you want to eliminate or simplify, and so you like to, again, so you can, yeah. This one actually does it a little bit differently. This one takes the validate function, moves it into this state, and then just, if it's, I combine these two, and if it's valid, I go down here. If it's invalid, I I eliminate that state. I just say invalid. And I should, as a response here, put issue error message. So there is a good reason to simplify this and to eliminate states when you can. If you are a requirements engineer, it's very good to do these reviews with these diagrammatic notations of these state machines and look for ways of improving them by simplifying the requirements, or certainly simplifying the potential design implementation by doing this. Okay. So finite state machines as a modeling tool, it is good for simplification. It's a great abstraction method, but for many real software projects, the number of states can become too big and needs to be abstracted to a smaller number. Now, that is true in large state machines, like for example, if you're trying to model the user interface, a complicated user interface where we may have hundreds of events and hundreds of states, state machines could become very large. There's a term referred to as state explosion, and what that means is that the number of states essentially gets very large or explodes and becomes very difficult to analyze systems like that. And so now the good news with this type of modeling approach is that you can abstract some of these state machines and eliminate some of the other unnecessary detail and be able to analyze the system from a different level of abstraction, which could be useful in certain cases. So, for example, if you showed, remember we showed this. We showed from my initial state, we showed quarter, quarter, quarter. Remember that? And then select. Well, that's fine. It shows the details of how this thing really works. What if I wanted to? If I wanted to abstract that out even more, because I wanted to view the system at a higher level of detail, maybe I'm concerned about the higher level system functions. I can also go like this: initial, what have I done there? Initial state, correct change, give them their code back to the initial state. I've eliminated all this stuff. What have I really done? I've abstracted out some things, obviously. I mean, I've created this thing called correct change, which is what? The correct change means 3/4 have been deposited. But again, see how I've kind of taken potentially a lot of states and just abstracted it out into now, a single state machine like this makes no sense. You can't really use this to understand anything about your software system. However, when you have systems, hundreds or thousands of states, these types of abstractions become very necessary. So for example, this is essentially counting quarters, 3 of them. What if I was trying to, what if I had a machine and it was I had to count up to 1 million, okay? Maybe there were timer expiries, timers expiring, a countdown of some sort. What if I had to count to 1 million? How would I do that with a state machine? Would I have 1 million states? Or would I instead have something like, instead of counting down 1 million events, what if I just had something like timer, count equal 1 million, and then have that be the event that triggers something, right? So abstraction is possible with state machines. It can be your friend. It can be very useful. I'm going to show you some more abstraction examples when we go a little bit further, but it's a way of simplifying the analysis. Now, the key for requirements engineer is you've got to get the model to the right level of detail. You want enough detail to make decisions and uncover hidden requirements. Too high level, you're not going to get anything out of it, useful out of it. Too low level, you might be stuck in implementation details. So you need to be able to look at this at the right level of detail when you're, when you're doing this model creation. So these modeling tools also allow us to detect mistakes. Now, by just reviewing it, the diagrams are good to review, and you can find mistakes. I mean, basically, what you would do with go back to my picture here. When you're doing this in kind of in the real world, you would look at this diagram and you talk your way through it. Okay, if I'm in this state, I get this, and I go here. Does that make sense? I'm going to go here. Okay, I'm going to transition here. Now if I get this input, I'm going to go here. And you can kind of talk your way through this. And by doing that, you could detect mistakes. Errors of omission, still difficult to detect. It requires concerted effort in questioning. That's true. Or you could take the approach of, okay, you know what? I'm going to look at every combination and make sure this matrix is filled out completely. And if it's filled out completely, I know I won't omit anything. I haven't forgotten about anything. I still have to look at correctness. Am I doing the right thing? But I can use this to determine that I don't have any errors of omission. Okay. Now there are actually tools that you could use to help you with this. There's a tool that now I believe is, I think the tool name, some of you may have used this tool, Rhapsody. This used to be from a company called iLogix. Now it's from IBM. Anyway, basically you could create in this tool state machines, okay? You can create these state machines. And then over here, you could create, let's say a user interface, just for sake of argument. So I can create, let's create a cell phone. I've got my cell phone, I've got, these different buttons, okay? And basically each of these buttons on a cell phone is an event, right? Pressing the green button or the red button, so you can, the numbers, each of these is an event. So what you can do in these tools is you can say, okay, I'm going to power up this system, and that power up is going to take me to this initial state. So basically when you hit the little power up button, you can graphically see the state machine that you've built transition to the initial state. And then if you hit another event, you can see the machine, I'm just going to draw some stuff. You can see the machine, okay, I'm going to hit this button, and the machine transitions to the appropriate state. Then when I'm in this state, I'm going to hit another button, and, it transitions to another. And you can see this thing, quote unquote, execute, go from state to state in real time as you hit the different buttons on the interface. You can see this thing transition, and if it transitions improperly, you might see a different behavior than you're wanting, and you can fix it. So these tools are, these are integrated development environments, and tools like Rhapsody allow you to do some fancy things with state machine creation. Then when you're through with that, this thing will spit out a template source code that you can then use or optimize or whatever you want to do with it. So there's tools out there that help you with creation of these state machines. You can use those. You can also use them to help you create these different scenarios and test cases. And then finally, rarely does a single input drive you through an entire application. As we saw, any complex application, you need a sequence of inputs to drive you through all these states. And we showed you, I showed you a sequence. I showed you sequences of, things like orders and, change, return and select, et cetera, that drive me through these applications. So this is a great tool for working those details at the right level of abstractions. Now, for many large commercial systems, this becomes very, very large. The key term for this in the industry is referred to as state explosion, and it's where, like, if you had a state machine, if you had a state machine that had a certain kind of behavior associated with it. And that state machine, if you said, okay, you know what, and let's assume this is a very simple state machine that handles some flight control system, and you had the requirement that said, okay, at any time the user can, or the pilot can pull the ejector lever to eject from the plane. Okay, let's say I had one requirement, R1. I had one requirement. What happens to this state machine? Well, it says at any time, so from any state, at any time, so the pilot can pull the ejector level, okay, to eject from the plane. So from that one requirement, we'd have to add another state, an arc from every state going to this new state. That arc would have on it, what would be the event that took me to this new eject state? It would be, ejector lever, okay? Ejector, So from every state, so I have to add 4 new events or arcs, one from every state, and then the response would be, it could be some kind of, emergency signal, whatever we want that output to be, and then a new state that handles the ejection. This state I could actually do this is where the behavior might actually be, the process of, eject the pilot from the aircraft. So one requirement adds a new state, and in this case 4 new arcs. But for every think of hundreds of requirements. You see how quickly this thing can explode into many, many states. So you have to be very, very careful about how to use these things. Again, you could use abstraction to help you with state explosion. There's another, so for state explosion, one approach to solve state explosion could be continue to use abstraction. There's some other techniques called state charts that essentially form really what they call super states. I'm not going to go into a lot of details on this right now, but it's a way of, really what a state chart is it's a state machine that eliminates some of the redundancy in all these arcs and states by simplifying the graphical expression of the behavior. It's still a kind of a state machine in essence, but it does a little bit more to simplify and abstract out some of the diagrammatic details. Okay, more on that a little bit later. So now this gets a little bit into testing, and I'm not going to talk about some of this. I'll skip some of this. Don't worry about augmenting state machines right now. We're testing. This is just an example of how, if you take this state machine, if you don't have these arcs defined properly, you're going to have mistakes in your table. You have to make sure you fill that in. We've already talked a little bit about that. Non-deterministic state machines. I put some notes in here, but this is something that just want to make you a little bit aware of. Like, think of something like a traffic light, where these lights can turn based on traffic scenarios and time of the day, or a phone switching system. We could turn these into deterministic machines by saying, a traffic light every 30 seconds or every time someone goes over a certain sensor in the road, it's going to have behavior. You can turn it into a deterministic system, even if events occur at random times. You can, for example, you can put the lights on timers. Phone switching systems can also be made deterministic, but there are situations where systems are more non-deterministic. These are things like games, where the next move in that game cannot be determined because you have to do something on the user interface or hit a certain button to determine what that behavior is. Or a GUI screen, where you're in a certain state of the system and you're not sure what the user's choice is next. In other words, it's non-deterministic. You cannot determine what the user is going to do next. Or even something like weather projection systems, where even the projection itself cannot be deterministic. So in these systems, the way we handle this, a non-deterministic state machine is just like a finite state machine, but one or more states, given the same input, may have more than one transition rule, like this one here, where I have a same event driving two different types of behavior, right? This non-deterministic finite state machine accepts strings of A's and B's and terminates with an A. These strings can be of length various lengths. You can define that. This particular case, again, the states are 0, 1, and 2. 0 is the initial state. 2 is the final state that we mark as 2 prime. The inputs can be A or B. The way we define this is if I'm in the 0 state and I get an A, I go to 1. If I get a B, I stay in 0. If I'm in 1, now I have to add 2 behaviors. If I get an A, I can either go to 2 or to 1. That's the non-determinism. That's where when it's non-deterministic, you can still model this as such, non-deterministic finite state machine. And that's just because we have more than one transition rule. And which is a rule that determines whether I do one thing or the other when A occurs. Okay. Most state machines will be focusing on will be more deterministic, but this is, for certain applications, this might be a better approach. Now, the Markov model, I'm not going to talk about Markov models. It's a way of dealing with more behavior associated with statistical nature and even statistical testing. I'm not going to talk about Markov models. Not in this class. It's there for your information. I'll let you read through it. I am going to skip this behavior, those slides, so don't worry about Markov models. This next section is really just, again, reinforced, some of the messages we've been trying to discuss already. You have a CD player user interface here, or you can call this a DVD player if you want to. This is getting probably get a little bit old as an example, but the point still is the same. This is from an excellent book called Constructing the User Interface with State Charts. So let's assume we've got this user interface. So what are the events on this interface that would be required for a state machine? Well, we have things like the play, pause, stop, forward, reverse, eject, and then those are inputs into the system. I'm displaying, or outputs could be the track number, the length of time for that track. Very simple interface. But now, if you're familiar with these buttons and what they do, and you're familiar with these track displays and time displays, so what if you had to write natural language requirements for the CD player to cover all the behavior? You had to write natural language requirements. What would they look like? Well, in this next slide, lots of detail. You may have to blow it up a little bit, but these 27 natural language statements form the requirements for that CD machine. I kind of showed you at the beginning. The user interface is the main source of behavior from a user's perspective. So these 27 requirements, if you will, can describe that complete behavior. Now, what I've got on the next slide is a state machine that describes not all, but a large amount of that behavior I just showed you on these 27 different requirements in natural language. You can see how terse this is. You can see if you can try reading this and making this out and being able to design a solution, reading these English or natural language requirements. I think that would be a challenge. As you can see, this is quite a challenge. But look at the picture. If I designed a state machine and I looked at the state machine and talked my way through it and reviewed it, I do believe a picture is, in this case, literally worth 1,000 words. And I think these things really help simplify the analysis process. So when you're developing these models, trying to derive and find hidden requirements for your system, talking your way through the model at whatever level of abstraction is necessary for you, this leads to, you can use these pictures to really help guide you. It's much easier to find problems when you're looking at a picture like this as opposed to trying to write everything down in natural language. So it's just to show you how, sometimes a picture is literally worth 1,000 words. Okay, so that's it on state machines. I've talked you through some examples, including the Coke machine, and there's, if you have any other questions on this, just let me know. Let's move on to decision tables. Now, decision tables, if you've got a complex, non-trivial set of business rules in the domain you're trying to describe, things that have a lot of logic in them. Users, humans are not good at logic. Okay? Excuse me. Users are not good at logic. Okay? We were not designed this way. Users are really good at emotion. For example, fight or flight. But when we were evolving, we had to know very quickly if there was a lion hiding in the forest ready to attack us. We needed to essentially turn and run or do something, and we had to do that very quickly. Okay? Logic was not the way we were wired. So it's very difficult for us to understand logic. When we're confronted with logic statements, we oftentimes have to, we struggle with them. We have to read them multiple times, what have you. So when you have non-trivial rule sets, you need to be able to look at a way of helping us understand that logic. When is a deposit needed? When is a supervisor's signature needed or a discount given? All these things could end up with complicated logic statements. Well, if this happens and that occurs and you're not doing this, then you can do that. So you can describe it in a programming language form. A table is even better because more stakeholders can probably understand it. So here's a case where, this requirement is basically allowing, R1. So the product shall suggest the following discount rates if a customer asks for a discount. Well, if the double room is used as a single, then the manager can give a 25% discount. If there's a family that needs more than one room, we can provide a 10% discount for additional rooms. You can have a discount at immediate check-in if it's before 6 p.m., the hotel is less than 50% booked, and it's fair weather. I can offer a 25% discount, but if it's before 6 p.m., the hotel is less than 50% booked, and it's bad weather. In other words, no one's going to walk around looking for another hotel if you don't give them a discount. Sorry, no discount. I know it sounds harsh, but if you're a captive audience, you'll be willing to pay more instead of walking around in the rain. So cases 1 and 2, let's say they cannot apply in the same state. I can't use a double room as a single and get discounts for multiple rooms. But anyway, so this logic, I can write it out as multiple requirements, or sometimes putting it into a single table adds a little bit of structure to this whole process. Now I could also use a decision table. I can consider these to be business rules of some sort. There could be more of them, but business rules, and this could be my decision table. So this basically is the same requirement, but now I've got the kind of the requirement aspects up here, and I've got the actual results or termination conditions at the bottom. And the way you would read this is kind of top to bottom. So you can basically say something like, if the room is used as a single and there's no additional rooms, the N for no, Y for yes. So I'm going to use the room for a single, no additional rooms. I'm going to give them 25% discount. If I'm not using the room as a single and I have additional rooms I need, 10% discount. And if I've got immediate check-in, it's before 6 p.m., the hotel is less than 50% booked, and it's not fair weather, it's bad weather, no discount. Immediate check-in, before 6 p.m., less than 50% booked, fair weather, 25% discount. I have the little question mark up here because this 25%, that 25%, maybe we catch ourselves and say, hey, are these the same thing? I put a question mark there. is room discount the same as early discount? This is a question that could trigger a different type of requirement. That's why I show it as a, hey, potential gotcha. I think I may have missed this one. Room is used for a single and additional rooms, error. In other words, that's not, either we're not going to have that as an option, or we haven't considered it, haven't defined it. Let's go look at that in more detail. So by going through this process, it kind of takes this logic and wordiness and puts it into a little bit more of a structure that someone could actually take this and go design a set of test cases for it, and probably do pretty well in trying to work through this. I mean, I can immediately see 1, 2, 3, 4, 5 test cases with different use case type results, and then I can probably try other combinations to make sure that maybe the system doesn't process them or we don't make them available, but it's a great way of doing testing. The pros and cons for this type of thing, they're good for describing business rules. Decision tables are good for these. For complex business rules, I can do a lot of good verification and validation. In other words, I can easily, much more easily design a set of tests for this, and I can also easily turn this into a program, software program. In other words, if I gave this to the design guys or the implementation guys, the developers, they would much rather have this as opposed to this, or even something less structured. This is easily, for them, this is nice logic-centric form that they can take and turn into a program. And then now rules expressed as programs with loops, so I'm going to loop, or recursion, which means basically one function calling itself, a function calling itself. That's much more difficult to use in decision table, because I'm calling into itself. You can't. It's hard to represent that in a table. So those types of rules are not suitable, but other basic logic rules, this thing works really well. Okay. Okay, so that's it for decision tables. Let's address one more topic tonight. Talk about activity diagrams. This is based on some information from Dr. Fayyad. And I want to talk a little bit through the activity diagrams as another way of looking at your system level behavior. Again, this is it's a use case type it's a UML diagram, but I want to use it in a more generic way. In other words, you don't have to use UML for this. This can be done with just non-object oriented, non-UML type tools. It's just a good view of software behavior. So an activity diagram describes how activities in your system are coordinated, which sometimes is very important to show that coordination between systems. Very useful when you know that a certain operation has to achieve some things. You want to model the strongest or the most essential dependencies between your system and other systems, and what order to go through doing certain things. So from an ordering perspective and interaction perspective, very, very useful, from a coordination perspective. Records a lot of the dependencies between the different potentially concurrent activities. For concurrent meaning which things can happen in parallel. What has to finish before I start something else? It's great for that. So it really is a workflow type diagram, and it's workflow is very important, very useful in the requirements process to again help look for certain potential hidden requirements or ill-defined requirements. You can show a simple notation. We've got blocks. Well, again, think of a kind of a flow diagram. We'll build this up. You have blocks, which are activities. Those activities are independent. They can be independent, or you could show, so this is pointing at different activities. You can have a transition between one activity and another. Now, this is similar to a state transition that we just talked about. And we can add some other properties to this, but it's a simple transition between, say, one activity. Again, right now, since we just started thinking about state machines, you might view this as a state, but in this activity diagram, this is more of a little bit more general activity that a software system would take. I'll show you that in more detail. These things could have decisions, and they can take many paths. One way of showing decisions is to have multiple outputs from an activity that are guarded or indicated which path you're going to take based on the value of something like X. I can have something like this straight out of the activity diagram, greater than 0, equal, less than, or I could send an activity, I could have an arrow pointing to a decision diamond and have that show the same thing. This would go to potential other activities in the system. Either way is really fine. There's also synchronization and splitting or forking. Bars that activity diagrams could need to represent. For example, this synchronization bar, thick line there, this one's a join because basically it shows two activities coming into the synchronization bar. They both have to get there. They both have to complete, in other words, and arrive here at this synchronization bar before you can continue. I'll show you more about that. Sometimes this is can be referred to as an and, this and that before we continue. You can also represent this as, if you represent it properly, this or this, and then we continue. And then this is also, this can also be used as a splitting bar where I get an activity in, transition from an activity, and I fork or split into two or more additional activities. These are both very useful. This XOR is another similar, from a diagrammatic perspective. This can continue on if you get one or the other, but not both. Then you continue on. One or the other, continue on. One or both. One or both, and both required before you continue on. You can add those properties to this as well. But normally, you would view this as join, which means they both have to arrive before you continue. And when this one finishes, you get two independent forks happening. A few others, we're going to have a similar start and stop marker from the state machines that you're used to. So those should look familiar to you. We are going to have introduce another part of the notation called swim lanes. These swim lanes, think of this as a way of separating out different activities from different parts of the system. In this particular case, this is showing different roles in an organization, developers, testers, markers. Each of them, so developers, we're going to describe all the activity in this swim lane. Testers, we're going to describe all the activities they do in this swim lane. Markers, all the activities in this swim lane. And occasionally we'll have to coordinate by sending information back and forth across these swim lanes and do some other coordination, which I'll show you in a second. So you could end up with a library type example where you have a activity that includes members and librarians, and you can see the swim lane that separates members and librarians. Think of time starting at the top, going to the bottom. Okay? Members and librarians. I've got a start indicator that starts this activity diagram. I make a decision, am I a member, am I a borrower or a returner? If I'm borrowing, then I'm going to go to the activity Find Book on Shelf. If I'm going to return, I go to Wait in Queue to return that book. Once I find the book on the shelf, I'm going to then go stand in that queue to get processed by the librarian. Both of these guys need processing by the librarian. So find a book on the shelf, wait in the queue, or if I'm just returning, wait in the queue. This is the line to see the librarian. Once I get to wait in the queue, that's an indicator to the librarian. This is, again, a synchronization bar that basically says when the librarian is ready, prepare for next member. When the librarian is ready and someone's in the queue, then I continue. So again, if someone's in the queue and the librarian is ready, I'm going to continue on. Am I returning or borrowing? If I'm going to borrow a book, I go to an activity where I record the fact that I'm borrowing it. I scan something in. Whatever's inside this activity is going to allow me to record the fact that I've borrowed a book. If I'm returning, then I'm going to do two things. I'm going to, this fork, I'm going to record the return, also put the book back on the shelf, and these could be done by different people, so I'm going to use it as a fork. When both those activities are done, the book is on the shelf, I've recorded that it's been returned, at least the way I'm describing this one. Then when both those are ready, I'm going to prepare for the next member. And then here, I will either, I can either go to the waiting queue. Eventually, I'll terminate if there's no other people in the queue, or if it's the end of the day, I can define this in a little bit more detail. But you can see how we, essentially keep doing this until we decide at some point to terminate. Okay. So what do we have here? We have activities, decision diamonds, synchronization bars for joining, fork, synchronization bars, all shown, and then we have the swim lanes. One swim lane, another swim lane, the start, the end. All these are shown in this simple example of an activity diagram. Those are all the major components you'd find. And you would do this, you can do this because you have decision points. You can represent multiple scenarios on an activity diagram. And you can have multiple activity diagrams. They're used to model the dynamic aspects of a system. Things happening dynamically as information flows through the system. It's essentially a flow chart. If you're familiar with flow charts from, they used to be popular a while back. They've been folded into these activity diagrams, but a flow chart is you can see the flow of information through this activity diamond. Flow chart is comprised of activities and diamonds, so it looks very similar to a flow chart, and it shows flow of control from activity to activity, activity to activity. Very useful for modeling business workflows and operations, and you can also really help understand requirements well by putting these diagrams together and studying them. They commonly contain, again, these states, activity states, action states, transitions, objects, which are in many cases similar to states. For object-oriented, these objects in here mean member and librarian. If you had a member object in your object-oriented system and a librarian object, that's what that means. Objects, transitions, states, or activities. The action states themselves they're atomic, so we can't decompose them. We do not want to decompose them. In other words, the work of the action is not interrupted. You cannot interrupt that activity until it completes. So these activities, think of them as once you start it, you've got to finish it. You can't interrupt, find book on shelf. You can't interrupt, these other activities. So it's not interrupted. Once they start, they stop. They can be decomposed. The activities can be represented by other more detailed activity diagrams. And at that level of detail, they can be interrupted. If this actually is a number of activities itself, you can interrupt after each one of those activities. So this decomposition, again, is the abstraction coming into play here. So, again, just, when the action or activity of a certain state completes, the flow passes immediately to the next action or activity. Those are basically the arrows that you see passing immediately to, okay? A flow of control has to start and end someplace. You see it here, it starts someplace, it ends someplace. Here's another view of some of these different definitions. So we have our start state, we have our action states here. We have a triggerless transition. You see here, there's no triggers on these things, right? You don't see a lot of triggers. Now, in some of these activity diagrams, what they like to show is across the boundary. See this boundary here? We have the swim lane. Anytime you see something coming across the boundary, they like to represent anything going this way across the boundary or that way across the boundary. There's some kind of data or an event that we can describe there when we talk about stuff going back and forth across boundaries. We'll talk about that later. So we have start state, end state, action states, and triggerless transitions within these activities. Again, simple example. For processing a deposit to a savings account, we start triggerless transition, display deposit savings window, that activity. The deposit savings button is pressed in the bank UI window that starts this. Then that finishes, goes to the account deposit, where I'm going to deposit the amount, then terminate. That's a simple activity diagram for processing a deposit to a savings account. Display deposit in the window, account deposit to the account, the amount that's been given, and simply end. Branching can be shown. Like I showed you, branching specifies alternate paths based on some kind of Boolean expression. Like I'm going to release a work order, and then I have to make a binary decision. The materials are ready, are not ready, or they're ready. These are referred to as guard expressions. These guard expressions are these Booleans that determine which way to go, one way or the other. That's the branch, obviously. It can have one incoming transition and two or more outgoing ones. It's a little bit cut off by the picture. In this case, not ready, I go to reschedule, or ready, I go to assign tasks. So here, a member arrives at an ATM machine, inserts the card, enters the password. There's a Boolean. Password is either accepted or not accepted. Boolean expression. If it's not, go back and enter it again. If it is, go to select the type of transaction, perform the transaction. Either there's no more transactions or there are more transactions, another Boolean decision, and then take the card and you're done. Okay? Simple way to reflect. I'm arriving at an ATM. I'm performing some set of activities, and then I'm leaving. I'm done. Joining and forking. So I'm going to use a synchronization bar to specify the forking and joining of the parallel flows of control, which is obvious by looking at these things. And we use these synchronization bars. It's just a thick horizontal or vertical line. You can represent them either way. When I've got one activity coming into a synchronization bar and then multiple activities out of it, that's a fork. There's one fork there. Here's another fork there. And then when I've got multiple activities coming into a synchronization bar, with one activity coming out that's a join. So I've got forks and joins. So I'm going to prepare for a speech. I'm going to decompress and do a gesture activity. At some point, that decompression, I'm also going to sync my mouth and stream my audio and join those together and clean up. That's an interesting way of representing that, but that's showing forks and joins in this one activity. Now, so a fork can have one incoming transition, 2 or more outgoing. Each of those outgoing is an independent flow of control. Now, again, conceptually, the way we do that, because these activities, we want them to be concurrent. Truly concurrent, which means you can literally put these on a different node of a multi-core processor. Or if you have one CPU, they're sequential, but they're interleaved. So you can, this can be truly, hey, put this on one core, put that on another core, or put them on my single core, but just interleave them, task switch them as necessary. It still gives you that concurrent, conceptually concurrent look and feel. And a join, can have 2 or more incoming transitions and only 1 out. So above the join, we have multiple activities that are associated with each of the paths coming in. Those are happening again in parallel. And at the join, there's concurrency. Concurrent flows synchronize. Actually, I'm sorry. There's synchronization, not concurrency. There's concurrency that comes into the join. They get synchronized. Each waits until all of them are there. When they're all there, then you continue on. So here's another example for processing mortgage requests. So I have this incoming document. I'm going to prepare my incoming documents, index those documents, make an electronic file, complete the request. Then concurrently, I'm going to check data for life insurance, and I can also in parallel draw up a contract for the mortgage deed, probably because they're not entirely related. Then I'm going to calculate data for the mortgage, paper, when I'm doing the contract deed, pay the provision to the insurance agent. So I do both these tasks. Maybe this is one person in the office building, this is another person in the office building, or there's different cores on a multi-core processor, or the same processor is doing both of these and interleaving them, but they both have to complete before you draw up the insurance policy. That's the join at the bottom. So you see the fork, you see the join, and if these are done by different actors or different objects, you can put these in different swim lanes to show that that's who's doing that. So again, you can see another the initial state there. You see all the different action states. You see the sequential branch with the Boolean expression, the fork, the independent concurrent tasks. You see the join, the bottom, and the final state. This finished construction, this is just an object flow. We're not talking about object-oriented right now, so don't worry about that. You can see the rest of this is pretty straightforward activity diagram. Now I could get a little bit more complicated. Here's one. I got a person starts this finding a beverage. If I find coffee, if I don't find coffee, that guard. If I don't find coffee, I go to another decision. Do I want a cola or no cola? If there's no cola, I terminate. If there is a cola, get a can of Coke, drink the beverage, terminate. That's if I go down this no coffee path guard. If I do find coffee, synchronization, that synchronization bar is actually a fork. I'm going to, again, in concurrency, I could put coffee in the filter, add water to the reservoir, and get cups. Now, I could do all this in parallel. Maybe I don't do it in parallel, maybe, but I could do something. I could actually do all these in parallel So if I had more people, I can get all this done in parallel, but after I put the coffee in the filter, then put the filter in the machine, and then once water is added, those two things have to complete, then I turn the machine on, brew my coffee. When the light goes out and I have my cups, I have to have both of those before I can pour my coffee and then drink it and terminate. So you can see how that flows. So it's a logical way of showing these concurrent activities that could happen. Not that they always will, but they could. They could be done by more than one person, by more than one processor. But it's an interesting way of showing where I can get concurrency. But then where do I have to sync up before I can go on as well? Another one, processing orders. I'm going to set up my order. If it's a single order, I'm just going to assign the seats, charge the credit card, and mail the packet. If it's a subscription, I'll assign the seats, but also award bonus points, debit the account. These are concurrent threads, as you can see. And then both those have to happen, assign the seats, debit the account, award bonus. When all that's done, I can mail the packet. Okay, just another example there. This is another example for a user interface where I could have a button that I press in that interface. That button that I press could take me down multiple paths: charge, checking, savings, withdraw from checking, withdraw from savings, balance inquiry. This is a button pressed on the user interface, or done, terminate. And you can see how that button that I press, I can use this to determine essentially which button that I press, and then terminate if I select done. The swim lanes, again, this focuses on a locus of activities. If I go back here, where was it? Here, I had it here. I'm going to go all the way back. So each swim lane, member, librarian, a locus. In other words, inside this swim lane, all of this activity belongs to the member. All of this activity belongs to the librarian. I've got decisions to make. I've got information to share between member and librarian across this swim lane, but all of this activity belongs to that that actor inside that swim lane, the locus of activities. To partition the activity states into these groups, each group that represents the organization has to be responsible for those activities. That's what we call the swim lane. It's divided from its neighbor by that vertical line I showed you. We're going to name it uniquely within the diagram, like member and librarian. Those swim lanes could represent real world things, like a member, like a librarian. It could be implemented by more than one class. Actually, just substitute software component in there. It doesn't have, we're not doing necessarily focused on object oriented. And each activity belongs to exactly one swim lane. Transitions may cross swim lanes. So again, if I quickly go back to that swim lane example, you can't have an activity that crosses the swim lanes. Only these transitions can cross. You can't have an activity that straddles the line, okay? That's the key thing there. So here's one where we have 3 swim lanes: customer, sales, stockroom. The customer is going to begin, request service. He's going to send an order. Think of this as data. Okay, think of that as data now, crossing this swim lane boundary, to a sales guy that takes the order. The sales guy takes the order and sends to the stockroom some order information. The stockroom fills that order, sends the order filled information back to the sales guy. The sales guy waits for the customer to pay. When the customer is paid and the order is there, the sales guy will deliver the order. That order shipment information will go to the customer, and that customer will collect the order. So now all we've added here is a box. Sometimes I don't even use a box. I just write the text on the thing that crosses the swim lane. So a little bit more information added here. One of them is data. So there's my data. You can put it in a box or you can just write it. The dotted line indicates that it's data. The solid line indicates that there's no data. It's just an event that shows completion. So when I finish paying, what this is saying is I don't send payment information over here. I just indicate payment has been done, an event has happened, and I go here. This is actual data that's needed in the system. Another, this is kind of blurry, office clerk, insurance agent, loan officer. You can again see it starts someplace. Activities are happening. Information is moving across the swim lanes. Each activity is uniquely in one swim lane. There can still be forks and joins that go between swim lanes, but each activity is only in one swim lane. So the pros and cons of this are, first of all, it's good for designing new activities into the domain. If you've got an existing application, it's good at specifying communication between the different technical components, even outlining the internal structure, although for requirements, we won't be spending as much time on that, the internal structure. It's more, more high-level requirements type of work. Validation, customers can actually read these things and understand them. It's got some cons. It's kind of poor describing the actual data communication between the actors. We're going to use data expressions to help us make that more clear. They do take up a lot of space. You can see how they kind of get a little bit messy. The flow chart can get a little bit messy and unstructured from a programming perspective. So although it's got some good aspects to it from a visualization perspective, you have to be careful that these things could get messy too. But it does convey a lot of very useful information. It actually displays, if you look at those things, activity diagrams, part of it is state machine between each of the swim lanes, the autonomous kind of state machine. It shows concurrency. It shows flow, the flow diagram, and even a little bit of data passing backwards and forwards between the different swim lanes. So it actually takes a lot of information, displays it in one picture. It is very useful for that, for that activity. And so these things are generally rich in information that is displayed, but it does, again, you have to be careful you don't overdo it from the, just from someone trying to read it perspective, okay? So that's, what we'll do is we'll stop there and, we'll continue on next week going through these different modeling approaches. There's several more we have to do, but that's a good stopping point. We'll pick it up next time with sequence diagrams, and we'll talk about those and several more left to go as we continue working through our modeling lecture here. So that's it for tonight, and we'll pick this up next time. Thanks very much. We'll see you during the next lecture. I couldn't find the. Right, thanks very much. Thanks for accommodating me. I'm glad to pack up and leave.
Right.
I'm thinking I
had other stuff going on tonight too.
Oh, okay. Yeah, I appreciate it. So this will be from. I'm going to be teaching live tomorrow. This will